Back in step 7, we practiced solving systems of equations in two variables, where we had an x and a y, two equations, and we solved the system. We can solve by graphing, substitution, elimination, matrix method. Now we have three variables, because a lot of times in real-world problems, you're not just dealing with two unknowns, you're dealing with three unknowns, and we need to be able to solve this. Well, if you think back to Algebra 1, you could solve equations with one variable. So you could solve for x or solve for the missing letter. We needed one equation. Back in step 7, when we needed two variables, we had to have two equations. So if we have three unknowns, x, y, and z, we're going to have three equations, three pieces of information. If we only have two details and three variables, we're not going to be able to set up a system or solve it. That would not be enough information. First, on our notes, you'll see kind of a visual approach to what this looks like. Each equation is now in 3D, not just 2 dimensions, but 3 dimensions. So each equation is not an equation of a line, it's actually an equation of a plane. And if three planes intersect, they intersect at one point, and we call that an ordered triple instead of an ordered pair. Sometimes they will intersect and form a line. That's when we end up with infinitely many solutions. And other times, all three planes don't intersect at the same spot. Sometimes it's because they're parallel planes. Sometimes two of the planes are parallel and they intersect the third plane, but the green and the blue don't intersect. Or maybe this scenario where we have the yellow and the blue intersecting, the yellow and the green intersecting, the green and the blue intersecting, but not all three in one spot. To solve a system of equations, it's really not too hard. We just have to eliminate one variable and then go back and substitute repeatedly as we continue to solve. So, for example, I'm going to mark my equations so I can remember which one's which. I have a yellow equation, I have a green equation, and I have a blue equation. If I just take these first two equations and ignore my third equation, I won't have enough to solve, but I could eliminate these and have just two equations in two variables. Let me show you what I mean. I'm going to pull off my yellow equation and my green equation off to the side. On this equation, I could easily eliminate the y variables if only this was a 2. And we can make that happen, if you recall, by just multiplying the entire equation by 2. So my first equation doesn't change. 3x minus 2y plus 4z equals 35. My second equation, I'm going to multiply each term by 2, so I get negative 8x, positive 2y, that's good, they're going to cancel, negative 10z equals negative 72. Now with the elimination method, the x's combine to become negative 5x, the y's cancel out, 4 take away 10 is negative 6z, and 35 take away 72 is negative 37. Now let's go back. We just used the first two equations to come up and eliminate y. Now we're going to grab the last two equations. I'm going to pull them off to the side. Negative 4x plus y minus 5z equals negative 36. In the blue equation, 5x minus 3y plus 3z equals 31. I want to eliminate the y because then I will have two equations in terms of x and z. So I wish I could eliminate the y's right off the bat, but I can't because I need this to be a 3. So I'm going to multiply the whole first equation by 3. Then the y's will eliminate. So when I do that, for my next equation here, I end up with negative 12x plus 3y minus 15z equals negative 108. And I'm not changing my second equation here. With elimination, I end up with negative 7x. The y's cancel. I end up with negative 12z and negative 108 plus 31 gives me negative 77. So now we've taken our system and we've come up with a new system. We have our pink equation in terms of x and z, and we have an orange equation in terms of x and z. That's two variables, two equations. So I'm pulling them off to the side. Pink equation, orange equation, and I need to eliminate. But none of the variables have opposite coefficients. But if I could just multiply this top equation by something to get negative 12 or positive 12, they would cancel out if this was a positive 12. I need to multiply by negative 2 to make that happen. So my new first equation is 10x plus 12y negative 37 times negative 2 is 74. Second equation. Oops, I just realized I wrote a y. That should be a z. And now I can eliminate my z terms. 10 take away 7 is 3x. 74 take away 77 is negative 3. Dividing by 3, x is negative 1. So think about what our goal was. Our goal is to find an ordered triple that satisfies this. We have one part of it. And you might be thinking, oh no, we're only a third of the way there. Well, yes, but the rest is much easier. From here, we're going to just go backwards. We're going to start with this x equals negative 1. And we're going to come back to either the pink or the orange equation and substitute. Since the orange equation is on the bottom here, I'm just going to do that one. I'm going to put a negative 1 for x and solve for z. Gives me 7 minus 12z is negative 77. Subtracting 7 from both sides and dividing by negative 12. Negative 84 divided by negative 12 is 7. So that fast, I have my next part. Z is 7, x, y, z. I now know what z is, and I know what x is. So I'm just going to bring it back to any of my first three equations, the yellow, the green, or the blue, whichever I choose. I'm going to sub them in. In fact, I'm going to move this ordered triple because it's kind of in my way. I'm going to move it down here. Negative 1. All right. So I'm going to rewrite this 5 times negative 1 minus 3 times y plus 3 times z equals 31. And solve. Gives me negative 5 minus 3y plus 21. Negative 5 minus 3y is 10. Negative 3y is 15. So y is negative 5. What this means is I found one point that I could plug the values into each, the yellow, the green, and the blue equation, and it would hold true. This is my solution. Now, some of you might be thinking, well, in step 7, when we solve two variable equations with two equations in a system, we just used a matrix. Couldn't we do the same thing here? And the answer is yes, absolutely. That's not a problem at all. Let's see what happens when we use the matrix method with this type of problem. So opening up our matrix, we want a new matrix. This is in Desmos, but you can do this on the TI. We have 1, 2, 3 rows, and we need an X column, a Y column, a Z column, and a constant. So that's 4 columns. And now we're ready to just type our matrix. To make sure you understand where this matrix is coming from, we can go ahead and write it in our notes. 3x minus 2y plus 4z is 35. Negative 4x plus 1y minus 5z is negative 36. 5x minus 3y plus 3z is 31. That's what we're typing into our matrix. 3, negative 2, 4, 35. Negative 4, 1, negative 5, negative 36. 5, negative 3, 3, 31. I want to row reduce echelon form, RREF, matrix A, and there's my answer, negative 1, negative 5, and 7. Much faster than doing it by hand. Much less work involved. One thing I want to point out is that if you can do this process by hand without the matrix, you can get some extra credit. Let's pause the video and try 1A and 1B and see what you get. You may use the matrix method if you prefer, or you can try it by hand. Hopefully for your answers, you were able to get 3, negative 2, negative 4 for the first example, and negative 6, 2, 8 for the second example. Let's try this next one together. In our matrix, we have 5x, 4y, negative 5z equals negative 10. Negative 4x, negative 10y, negative 8z equals negative 16. 6x, 15y, 12z equals 24. If I copy that matrix down that I just typed in, 5, 4, negative 5, negative 10, negative 4, negative 10, negative 8, negative 16, 6, 15, 12, 24. When we reduce this matrix, we get a new matrix. I'm just copying down what the calculator is giving me. That's a lot of decimals, and I'm not writing all the decimals. Okay. This is a problem. Remember, when we want to get one solution, we need to have zeros everywhere except for the diagonals where we have just ones. That's the only way to come up with one solution. We don't have that here because right here we have a 0. But what we have looking at this entire line is a true statement. 0 equals 0. That's what that means. 0 equals 0, which is true. And if I look at the lines above, I have 1x minus 2.4 something z equals negative 4.8 something. That's true. That's allowed. And same with the second line. No false statements are happening there. So our answer for the first one would be infinite solutions. Let's look at our next example. Again, making the matrix. It's nice because they're given to us in the appropriate form. That's not always going to be the case. Sometimes we're going to have to make sure we have A, B, and C on the left and our number by itself on the right. But so far we haven't had to do that. Let's type this into our matrix calculator. We have negative 6, 9, negative 12, 21, negative 2, 3, negative 4, 7, 10, negative 15, 20, negative 30. Notice what we get when we reduce it. We end up with 1, 0, 0 in the first column, negative 1.5, 0, 0, 2, 0, 0, 0, 1, 0. This line is true. 0 equals 0. But if we look above to the line right before that, we have 0 equals 1, which is not true. And when that happens, we end up with no solution. Finally, let's take a word problem with 3 unknowns and use what we know about solving a system of 3 variables to come up with a solution. Here we have a stage, and we have seats that cost $120 in the A range. And then the next section are $45 seats. And then finally out in the lawn, you pay $35. So much cheaper out in the lawn. So what 3 things are we talking about? We're talking about seats in area A, seats in section B, or lawn seats. So I'm going to define my variables. X, Y, and Z. Now, just like before, you can use A, B, and L for lawn if you prefer. Let's see. They want us to determine the number of seats in each section that were purchased, or the number of tickets in section A, the number of tickets in section B. So this is the number of seats in A. This is the number of seats in B, and these are the number of lawn seats. So let's take the information that we've been given and write an equation. We know the value of A, the value of B, the value of C, and the total value. Value of A, B, C, total value. So we can write an equation representing that. We can take 120 times the number of X seats, 45 times the number of Y seats, and 35 times the number of lawn seats. And altogether, it made a profit of $962,500. Now remember, 3 variables, we need 3 equations, and that's just one equation. We also know, though, that all 20,000 seats were sold. Okay, 20,000 seats total. That means if I take X, Y, and Z and add them all together, I should get 20,000. Okay, that's good. There's one little tidbit of information that we haven't used yet, right here. There are twice as many seats in section B as in section A. Twice as many seats, so there's more in B. If I take B, I would need to take twice A to get B. So that's my third equation. Now, if we want to put this into a matrix, we're going to need to move things around in this third equation. The first one's pretty straightforward. 120, 45, 35, 962, 500. The second one's pretty straightforward. 111, 20,000. But in this last equation, I need x on the left. I need to subtract 2x. So I have negative 2x, 1y, no z, because there's no mention of z in this equation, and it would equal 0 then when I move this over. In fact, I'll write it in parentheses here. This is negative 2x plus y equals 0. That's another way of writing this same equation. Okay, let's put this through Desmos and see what we get for our answer. I'm going to just keep modifying what I already have here so I don't have to retype too much. All right, when I do that, here's my new matrix. 2,500, 5,000, 12,500. And that fast, I forgot what it was. Flip back, 12,500 lawn seats. Okay. So that means that we sold, or they sold, 2,500 seats in section A, 5,000 seats in section B, and 12,500 lawn seats. We will do a lot of these other examples in class, but this just gives you enough information to get you started on solving 3 variable systems